So moving on, part 3 is going to be Taylor's formula for functions of several variables. So last time f was just a function of a single variable x, and now I'm going to let x be a vector. So you can think of x as x1, x2, up to xn. And f is still going to be a real valued function. So whatever comes out is, I'm assuming, is scalar. And a linear approximation of f around a point A. So A has to live in the same space as x now. So if x has n components, then A has to have n components as well. So if it was a point in the plane, you'd need an x coordinate and a y coordinate. And for x, then you'd need an x coordinate and a y coordinate for the point A as well. And then linear approximation around the point A, it looks a lot like the Taylor polynomial for the function of a single variable. So I have one point, f of A, where I know what the function value is. And then I'm just going to add a linear approximation. So for each of the directions, I just multiply the distance in that direction, so that's xi minus a, times the partial derivative, so the slope in that direction, which is the partial derivative of f with respect to that direction, and then evaluate it at the point A. And again, we end up with the result that if the second order partial derivatives are continuous, then we have a second order approximation. So if I make this linear approximation, so order 1 Taylor polynomial, but for a function of 2 or more variables, then f of x, so this is the thing that I'm trying to approximate, is equal to my approximation plus a term that behaves, and now I have to be a little bit more careful about how I write quadratics. So what I'm looking at here is x is a vector and a is a vector. This symbol, the two vertical parallel lines on each side, that just meant the length of the vector, so the Euclidean length of the vector. And because that length is squared, this is big O of x squared, essentially, as x is going to a. So I still have the same quadratic sort of error property for this linear approximation that I had when I had a linear approximation for a function of a single variable. And it also turns out that because this big O is kind of taking care of any, it's taking care of these constants of proportionality, you can also think about this as just the sum of the individual components squared. And also for the quadratic approximation, so now that this is getting a bit more complicated, so I have f of a is my constant, so that's the one point where I know what the true function value is. I have the linear approximation that's the same as in my linear approximation up here. And now I have to do all of the mixed partial derivatives to get my quadratic term. So if I have a function of n variables, I have to sum I equals 1 to n and j equals 1 to n, and then all of the mixed partials times the distance in each of those directions. And then we have, because of just the definition of the Taylor polynomial, I have to have this 1 over 2 factorial here. And so hopefully you're starting to recognize that when I see big ugly sums like this, I can benefit from using vectors and matrices for my notation. So hopefully that's what's on the next slide. Ooh, good guess. So let's let d of f of x, so this is the gradient of my function f, and it's going to be a function that I can evaluate at a point x. And it's just defined to be the first partial derivative, the second partial derivative, and so on in a row vector. And so it ends up being, for a function, a scalar valued function of n variables, I end up with a row vector with n elements in it as the gradient. And then if I define x minus a, so remember for vector addition, we can do the addition element-wise. So x minus a is just going to mean this vector. So I can actually just do that addition, and this is a vector of a column vector, so it's got one column and n rows. And then I end up with, anyone remember what this is called? Hessian, good, okay. The Hessian of x, which is, so I take the gradient, and I kind of imaginarily put that across the top row. And then I just take the derivatives with respect to the x in each column, or sorry, in each row, and that gives me now a matrix of partial derivatives. So the mixed partial derivatives of the function f of x. And now that big ugly formula I had at the bottom of the last slide, I can now write that as, so I have to evaluate my function at the point where I know still. And then since the gradient is a row vector, I'll write a row times a column. So it basically is just become the dot product of this with this. But I can write that out using matrix notation because I've made the gradient a row vector. And that's a big O of x squared approximation. Then I can also write the quadratic Taylor approximation. So the first two terms are just what I had above. And then it turns out that that big ugly sum can be expressed in matrix vector notation as x minus a transpose. So that's this vector here, but transposed, because I want it to be one row times n columns. Then I'm going to multiply it by an n by n matrix. And then finally, I'm going to multiply it by a column vector. So that's an n by 1 matrix. So this whole thing is going to end up being a 1 by 1 quantity. So it's a scalar quantity. And what's left over is going to behave like x cubed. So as x is getting closer and closer to a, my quality of my approximation is getting better at a cubic rate. And so just as an example, let's consider a function of two variables. So I want to make a linear approximation of a function f with two variables, so x and y, around a point AB. And so all I end up having to do, I have whoops, I think I wrote this backwards. Oh no, sorry. It's one thing at a time. So here x is actually the number x. It's no longer the vector like it was on the last slide. And b and y are also just numbers. So all I'm doing to get a linear Taylor polynomial, I'm taking the function at the point where I know the true function value, ab. Then I'm making a linear approximation by the change in the x direction, so how far away x is from a, so that's x minus a, times the partial derivative of f with respect to x evaluated at ab, so that's the slope in the x direction. So that's just a linear approximation in the x direction. And then I do exactly the same thing here, but in the y direction. So this is how far away y is from b, times the slope in the y direction. And then what I'm going to end up with, when I look at the convergence properties here, it's a quadratic. It has quadratic convergence properties. So as x is getting closer to a and y is getting closer to b, the error term is big O of x minus a squared and big O of y minus b squared. And in matrix notation, I can just write this out. So remember, the gradient here is a row vector times a column vector. So those are conforming dimensions. So this, I just have to do matrix multiplication, but it's the same thing as a dot product. And then I still have my error term, but at least I kind of understand, it's not a bound, but I understand its property as I'm getting closer and closer to the point AB. Then if I want to add a quadratic term to my approximation, so this is getting pretty yucky here. So the first row here is just the linear approximation I had from the previous slide. Then I need to split up the, so there's going to be 4 possibilities, but the cross term, which I have on the third bit here, x minus a. Oh dear, I forgot one of my derivatives in the fraction. So I have x minus a squared divided by 2 factorial. So I need to have this 2 factorial in the denominator because this is that's the definition of the Taylor polynomial. And then I need to multiply that by the second derivative of f with respect to x, evaluated at the point AB. For the cross term, I have x minus a times y minus b. So this partial with respect to y was supposed to be in the denominator here, but I think I missed a bracket when I was typesetting this. So this is supposed to be the mixed partial derivative evaluated at AB again. And there's no 2 factorial in the denominator here because this one shows up twice. So I actually have an x minus a times y minus b plus a y minus b times x minus a. But because that's a symmetric term, I have 2 of those divided by 2. So that knocks out the 2 factorial that you would expect to find in the denominator here. And then finally, I have the y term, so y minus b squared divided by 2 factorial times the partial derivative of f, the second partial derivative of f with respect to y, evaluated at the point AB. And then what's left over should be order x cubed terms. So as I've added one more term to my approximation, then the error is now behaving as a cubic. And I can write this in matrix vector notation, so it simplifies quite a bit. I have f of AB, so that's just my function again. The linear term, then the quadratic term, and then again, these things should have been to the third power for the cubic error term.